Okay, we have this interesting formula here on the board for cotangent of x, and we have it equal to 1 over x plus the sum from n equals 1 to infinity of 2x over x squared minus n squared pi squared. I've already derived this once using the digamma function, or something really similar to it. It's a little bit different where it was going from minus infinity to infinity. In this video, what I want to do is do it a different way using the sign product formula. And of course, like I said, it's going to look a little different in the end. Okay, we have here over to the right our sign product formula. We've used this in a couple of previous videos. Now this is going to be pretty nice, but I think for a starting point, I don't really want this x here on the right side for what I want to do. So let's actually divide that off. I can just divide by x on both sides. So now instead we'll have an expression for sine x over x. And of course we'll cancel this here and here. And let me just clean it up to make it all neat. And then from here, let's just take the natural log on both sides. This is kind of a similar method I think we use to the, I want to say the digamma reflection formula. So if we take natural log on both sides, we can go ahead and use log properties, especially on the left side to start. So I can break that up, and for this I can write it as natural log sine x minus natural log of x. And then let's just leave this, take the natural log of the whole thing for now over here on the right. Now on the right side here, we're summing up an infinite number of terms. This is all within the natural log here. So this is kind of something like if you had natural log, it's an infinite expression, but if you had something like natural log a times b plus c, with log properties, we could break that up like ln a plus ln b plus ln c. So doing the same thing, what we'll do is we'll turn this into a sum. It's going to be each individual term with this as the input. So it's going to be natural log 1 minus x squared over n squared pi squared. But we're going to be summing up an infinite number of terms. So I can write this as the sum from n equals 1 to infinity. But then from here, we can just differentiate both sides. So we're going to have, let's see, we'll write it as dx over here. Same thing on the right. So then on the left side, when we differentiate natural log sine x, we're going to have 1 over sine x. Chain rule on it, that's going to be cosine x in the numerator. Over here, derivative of ln x is just going to be minus 1 over x. On the right side, before I differentiate this, first what I want to do is let's get a common denominator here. For 1, if I write 1 as n squared pi squared over n squared pi squared, then when we bring this together with the common denominator, it's going to become n squared pi squared minus x squared over n squared pi squared. But this is all inside the natural log. So then splitting this up with log properties, what's going to happen, we get natural log n squared pi squared minus x squared, then minus this piece natural log n squared pi squared. So going ahead and differentiating, we'll differentiate inside the sum. So we're going to have this sum from 1 to infinity. And then we're differentiating all this stuff. But when we do it, notice n squared pi squared is a constant. This whole thing's a constant. So when we differentiate, this whole part's going to 0. We just need to worry about differentiating this. We get 1 over n squared pi squared minus x squared. Then chain rule, but that part is just going to be constant again. So this is just going to be minus 2x here. But then from here, let's just add 1 over x on both sides. Add it over here. And actually when I do it, let's bring it in this spot just because I don't want to make it look like it's inside the sum. So on the left side, this is going to cancel out. But after this cancels out, we're just going to have cotangent of x on the left side. The right side is going to become 1 over x. Let's bring the minus sign in front of the sum, and we're going to have minus this sum of 2x over n squared pi squared minus x squared. And that's going to be our formula, the same thing we have up here. So this thing is pretty nice. In the other video, I'll just show really quick, I had a different expression where we're going from minus infinity to infinity. So one thing you'll notice about this formula is it does look different than what we had in that other video when we were summing from minus infinity to infinity. But it is very easy to go from here to here, or vice versa, of course. What happens, maybe starting here, you'll notice we've got a difference of 2 squares in the denominator. So you can easily factor this as x plus n pi times x minus n pi, just reversing the sign on it. Then from there, you can do partial fractions on it and get two sums. I think one is going to be like this. The other one's going to be x minus n pi. If you reverse the sign on it, like kind of just doing a substitution on the n, you can have all the positive terms, all the negative terms. But then one thing that we're missing is the n equals 0 term. Well, that's this thing right here. Because if you have, actually just take this, for the n equals 0 term in here, what's going to happen is this goes away, and now you just have 1 over x at just one term where the n is gone. So at n equals 0, this thing is 1 over x, and that gives us this piece right here. And so another way to write this is you could have it separated into all the positive and all the negative terms. Like you could have one sum going from 1 to infinity, and then you could have another sum going from minus infinity to minus 1. Although it's a little tricky because when you think about the harmonic series, for the harmonic series, it's 1 over n. This is kind of similar to that. If you think of x as a finite value, even with the pi on there, it's a lot like this, but this thing's divergent. So we do get into some trouble when we do this kind of thing. So anyway, it's more compact this way, but there is some sticky issues. So, okay, that's it for today. Thanks everyone for watching. Have a good day.